Hello, I'm Walter Mataifa, and this is a presentation on Control Systems 3, which is offered in the Electrical Engineering Department at Cape Peninsula University of Technology. In this presentation, I'm going to go through what we have previously covered in this module, starting with the control system stability. So, as we have previously discussed, stability is one of the most important characteristics of a control system. Besides stability, transient response and steady-state accuracy are also important. So in this topic, we basically look at how we analyze the stability of a control system and the various approaches that we can make use of to analyze the stability of a control system. So just to keep in mind that the approach to the analysis of the stability of a control system is dependent on the type of system that we are looking at. So a system can be linear or non-linear. It can also be continuous or discrete. And in this topic, we are going to focus on continuous, linear, and time-invariant systems. So one way that we can define the stability of a system is to look at the response of a system. And a system response can be thought of as having two components, that is the natural component as well as the forced component. So one way to define the stability of a system is on the basis of its natural response. That is the natural component of the response of the system. And based on this definition, we say that a linear time-invariant system is stable if the natural response approaches zero as time approaches infinity. It is considered to be unstable if the natural response grows without bounds as time approaches infinity, and we would say that it is marginally stable if the natural response neither decays nor grows but remains constant or oscillates as time approaches. So that is one way of characterizing or defining the stability of a control system. We can also define the stability of a control system based on its total response rather than just the natural component. And in this case, we can say that the system is stable if every bounded input yields a bounded output. And very often this is referred to as a Bible, that is bounded input and bounded output. Then it would be unstable if any bounded input yields an unbounded output. Okay, so basically the kind of a definition that we have been looking at is the one that looks at the time response of a system. And we would say that in the case of an unstable system, we find that the time response actually grows continually, or it's got transients that grow without bound. So we find that the whole the system never really reaches a state. Okay, So the question that was asked in class is, what is wrong with the instability of the system? And the simple answer is that when a system is unstable, we cannot control it. We are not able to actually command um, the output of the system to be to follow a certain trajectory. So that is why stability is a very important characteristic of a control system, because if a system is unstable, then it is also uncontrollable. Okay, so as we have seen already in a previous course, a linear time invariant system can be analyzed, the stability of a linear time invariant system can be analyzed based on the location of the closed loop pause. Okay, so the question is, in what cases is a system unstable based on the location of the closed loop pause? So we look at an example of a stable system. This is the block diagram of the system, and on the right hand side we see the location of the pause. And what we notice, this is the location of the closed loop pause. What we notice is that all the closed loop pause are on the left half plane of the complex plane, and at the bottom here we see the time response of the system to a step input. So we can see that this is stable because it has got decaying transients. We can see that in the steady state, as time approaches infinity, the output is actually bounded. If we think of the definition based on the bounded input and bounded output. Okay. Then we've got another example. The block diagram of the system is given again. Block diagram on the left, the pole location on the right, and the time response at the bottom. So what we notice is that the time response of the system actually has got growing transients. We would expect that as time goes by, these transients are going to continue increasing in magnitude. And what we notice about the location of the poles is that we've got some closed loop poles that are on the right half plane of the complex plane. So by this, we actually see that based on the location of the closed loop poles, the requirement for the stability of the system is for all the closed loop poles to be on the left half plane of the complex plane. Okay, so that is one approach for determining the stability of a control system. And we've got a problem presented to us here. How do we determine whether the following system is stable? Obviously, we can consider the location of the closed loop poles. But what do we have to do in that case? The stability in this case has to be determined based on the location of the closed loop poles. What we have here is the open loop transfer function. So firstly, we would need to determine the closed loop transfer function, and this is the closed loop transfer function. So this requires us to work out the roots of this denominator polynomial, which are the poles of the closed loop poles of the transfer function. And by this example, we see that it is not always very convenient to determine the stability of a system based on the closed loop pole location, because this requires us to determine the closed loop pose, which may be quite cumbersome in the case of a higher order system. So is there another way that we can determine the stability of a system without having to work out the exact pole locations? And this is what we are going to look at next. So there is the Routh-Hurwitz stability criterion, which enables us to determine the stability of a system without having to calculate the exact location of the closed loop pose of the system. So the Routh-Hurwitz criterion tells us the distribution of the poles, which means it's going to tell us how many poles are on either side of the imaginary axis of the S-plane without having to tell us the exact location. Okay, so how do we use the Routh-Hurwitz criterion? The first step is to generate the Routh table and then interpret the Routh table. That is going to tell us whether the system is stable or not. Okay. So besides that, the Routh-Hurwitz criterion also enables us, we can use it as a design technique, as I am going to highlight a bit later. Okay. So on this slide, we are given basically how we would generate the Routh table. The Routh table is generated based on the closed loop characteristic polynomial of the system. So what we see here is we have the closed loop transfer function, and the closed loop characteristic polynomial is basically the denominator polynomial of the closed loop transfer function. So we are going to use the coefficients of the closed loop characteristic polynomial to generate the Routh table. And the procedure is quite simple. Firstly, we need a label column in the Routh table, and this basically lists the powers of S of the characteristic polynomial in descending order. So the example system that we are given is a fourth order system. So we can see that the first label there is S to the power 4, and that goes sequentially in descending order right up to the constant, which is S to the power 0. Okay. Once we've got the label column, now we can focus on the rows of the table. Okay, so the first two rows are always based on the coefficients taken directly from the closed loop characteristic polynomial. And the rule here is that for the first row, we always start with the coefficient of the highest power of S, and then we list the coefficients, always skipping one element or one term. So you can see here that we started with the highest power of S, and its coefficient is a subscript 4. We skip the next term, we go to the power of S squared, the coefficient of S squared. We skip the next one, and we go to the coefficient of S power 0. So the elements in the first row are a subscript 4, a subscript 2, and a subscript 0. And for the next row, we simply take the coefficients of powers of S that we skipped in the previous step, which is a subscript 3, a subscript 1, and since we do not have anything following a subscript 0, we just put a 0 there. Okay, So always the Routh table, that is how we started. The first two rows are always based on the coefficients taken directly from the closed loop characteristic polynomial. Okay. Now to generate the elements in the subsequent rows, this is what we do. So for the third row, the elements of the third row are based on the previous two rows, which is row 1 and row 2. And the element B1, for example, this is just the determinant or the negative of the determinant of the matrix that is made from the previous two rows, and that is the columns that are right above and to the right of that element. So if you look at this determinant, the way that it is created, we take this column and the one to the right of the element. So it is the negative of the determinant of that divided by the element that is just above that is in the row just above the row that we are working out the element. Okay. We would do the same for the other elements of this row. Now for each of them, the first column is always the first column, like A for A3, and the second column is always to the right of the element that we are working out. Okay, so for B2, we basically take that column and that column which is to the right of B2, and we always divide, sorry about that, we always divide by the element that is in the first column in the row that is just above the ones that we are working out. Okay. So that is how we would work out B1, B2, as well as B3. And that follows on right up to the last one. So for example, again here, this is the determinant, the negative of the determinant of the matrix that is made from the previous two rows. So in this case, the first column is A3 and B1, that is in the first column. The second column will be A1 and B2, because that is the column that is to the right of the element C1 that we are trying to work out. Okay. Just as we have covered in class. Okay. So here we look at an example. We are given the block diagram of the control system, and as I mentioned earlier, we always use the closed loop transfer function to generate the Routh table. So given a system like this, we first have to work out the closed loop transfer function, then we can draw up the Routh table. So this is what it's going to look like. Following the procedure that was outlined in the previous slide, we end up with a Routh table that looks like this. So now once we have generated the Routh table, the next step is obviously to interpret it. How do we interpret the Routh table? We, as I mentioned earlier, the Routh table tells us the distribution of the closed loop poles of the system. How many poles are on the left half, how many are on the imaginary axis, if there are any, and how many are on the right half plane. Okay. So the interpretation basically tells us that the number of closed loop poles that are on the right half plane is equal to the number of sign changes in the first column of the Routh table. So and this is going to get a bit clearer when we look at the example that we were looking at previously. So based on the criterion that we looked at earlier, we saw that the system is stable if there aren't any closed loop poles on the right half. Then that means that the system will be stable if we do not have any sign changes in the first column of the Routh table. Okay, so looking at the previous example, you will notice that we only focus on the first column. Having generated the Routh table, we just focus on the first column and looking at whether we have any sign changes. Okay, so we can see here that from the first row to the second row, both values are positive, so we do not have any sign change. But from the S2 to the S1 row, we see that we move from 1 to negative 72, which means there is a sign change. And moving from the S1 to the S0 row, we are moving from, we go from negative 72 to positive 103, and that is also a sign change. Okay, so this tells us that we have two sign changes from positive to negative and negative again to positive. So according to the Routh-Hurwitz criterion, it means that this system, because it has got, remember, the number of sign changes tells us the number of closed loop poles that are in the right half plane. So this system has got two right half plane poles, closed loop poles, which means that the system is actually unstable. Okay. So we looked at in class we did consider two special cases in the generation of the Routh table. We basically come across we may come across one of the two special cases. The first one is that we may have a 0 only in the first column of the row. And the second case is that we may have zeros in every column. Basically, that means an entire row of zeros in the Routh table. Now, obviously, these two cases pose a problem for us, as we are going to look at now. So the special case one, when we have a 0 only in the first column of a row, as you may have seen, having a 0 in the first column is going to give us a problem, because when we are computing the elements in the subsequent rows, we need to divide by an element in the first column. So this would lead to a case where we need to divide by 0, and obviously that is going to give us an undefined value. So what we do in order to prevent division by 0, we basically substitute a 0 by epsilon, which we consider to be a very small number that is approaching 0. And that will allow us to carry on with the Routh table generation. Then we can consider further the implication of what we end up with. Okay, so to illustrate, we've got an example here. So in generating the Routh table for this system, this is the closed loop transfer function. We in the third row, we end up with a 0 in the first column. And if we were to move to the to the fourth row to determine this number, we would have had to divide by 0. All right. So what we do basically is we substitute 0 by epsilon, and we carry on with the computation of the other elements of the Routh table. And once we have done that, we are done with determining the other values of the Routh table. Then we could imagine that epsilon is a very small number. It could be positive or negative. Let's assume that epsilon is a very small positive number. Okay, if we make that assumption, this is what we end up with. It's illustrated for us here. If epsilon is a very small a positive number, when we substitute a very small positive number into this term, the whole term is going to evaluate to negative. If we do the same for this one, we are going to end up with a positive number. And this is not dependent on epsilon, which is obviously positive. So what we notice here is that we actually have two sign changes from positive to negative and negative to positive, which means this system has got two poles, two closed loop poles on the right half plane. That is if we consider epsilon to be a small positive number. But even if we were to consider it to be a small negative number, we would end up with the same number of sign changes from a positive to negative, and then again a negative to positive. So it does not really matter whether you assume epsilon to be positive or negative. We are still going to end up with the same number of sign changes in the Routh table. Okay. Then the next special case is when we have an entire row of zeros. This requires us to basically, as illustrated in this slide, we need to determine the auxiliary polynomial. Okay, so the procedure basically is we form the auxiliary polynomial using the row that is just above the entire row of zeros, right? Then we differentiate the auxiliary polynomial, and the coefficients of the derivative of the auxiliary polynomial is what we substitute for the elements where we have an entire row of zeros, and then we can complete the Routh table. Okay, so if we end up with no sign changes after doing that, then it means that the system, we do not have any right half plane closed loop poles, and therefore the system is stable. Okay, so that's basically the gist of the Routh-Hurwitz stability criterion. As we looked at in class, we are able to determine the pole distribution based on the Routh table, and we looked at an interesting example. We did look into details this example. I'm not going to go into it in this presentation, but basically it is something that you need to know to be able to determine the distribution of the closed loop poles of the system based on the Routh-Hurwitz stability criterion, which means you would have to determine how many poles are on the left half plane, how many are on the right half plane, and whether we have any poles on the imaginary axis. Another thing that we looked at in class is when we are given a system with an undetermined a gain value, then we have to use the Routh-Hurwitz criterion to determine the limit on the value of k for the system to remain stable. Okay. So again, we did look at this example in details in class. I'm not going to go into it here, but just to remind you that this is something that you should be able to do. Okay, so this was basically an overview or a recap on what we covered under the topic of a stability analysis and determination for linear time invariant systems. In the next presentation, we are going to consider the next topic that we have covered in class, and that is the topic of the steady state error. Right, thank you very much.